Hello everyone, welcome to the chapter-wise series of P4. Today we will be doing chapter number 6, integration. So this chapter will be divided into two parts, and this is part number 1 of chapter 6, integration. Let's go. So first of all, to start with some prerequisites, we should know what integration looks like in terms of x and y. For example, if there is a function y equal to x squared, we know that the integration of y with respect to x, indefinite integration, looks somewhat like this. Y equal to x square, we substitute x square in terms of in the place of y, and then we have x, we're integrating in terms of x, we raise the power by 1, and we divide this entire thing by the new power and add a constant, since it's an indefinite integration. If it were a definite integration, then we would have put the limits and ignored the plus c. Okay, so these are some prerequisites. I hope that we know all of these things. If not, please revise the integration chapter and get some knowledge, and then we will start with this video. So moving on with the new concepts of this chapter, what we have new here is parametric integration. So we have parametric equations, right? Parametric equations are equations which are linked to a parameter. So usually what we see is something like y equal to x squared plus 2x. This is a Cartesian equation. That's because it contains only x and y. However, if x and y are connected through some parameter, and that parameter can be t, then it is called a parametric equation. For example, this is a parametric equation where we have the parameter as t. Okay. Now, how do we do a parametric integration? In this chapter, I will be showing you the examples, and if you need help with any particular math of a particular exercise, you can comment and I will solve that exercise for you or solve that particular math for you. That's because it's not possible for me to do all the math. So I will only do the math which you request me to do. The exams are coming up, so I hope this helps. Starting off with example number 1, the simplest example. We have x equal to t and y equal to 3t squared. The idea here is that the paragraph above says that for integrating, we have y, integrating y with respect to x. Okay. So the problem here is that we have expressed y in terms of t and x in terms of t. So we need to integrate in terms of t with respect to t, not with respect to x. So what we have to do is, y is a function with respect to x, so we put y as it is, but we can't keep dx here. We have to put dt. In order to do that, what we have to do is, we put this dt. We have to put dx by dt into dt. dx by dt into dt. So let us see this example to see how exactly this works. We have x equal to t, so dx by dt equals 1, right? So we have dx equals dt. So the purpose of this is to substitute the dx from our integration. And we have y equals 3t squared, and this is what it is. We don't have to do anything with this. As for I, we integrate y with respect to dx, and y in our question is 3t squared, and dx is exactly dt in this simple example, but it won't be dt all the time, as we will see in the following example, and then we just integrate with respect to t. However, we have to put the limits, and in this question they have set the limits that the limits are t equal to 1 to t equal to 2. So they have set the limits very nicely. So we have t equal to 2 to 1, and after integration, now it has become a very simple definite integration. We can do it, and then we get the value, which turns out to be 7. So I will not move forward with the explanation of how we come to 7 from this step. I think this is very simple. I will move on to the next example. In example number 2, we have x and y in terms of t, but the case here is that this time dx will not be equal to dt. Dx will have some t function, and then we will have dt. So let us see this example. So an integration looks like this, integrating y with respect to x. Now first of all, we have to determine what we can put instead of dx. Y we already have in terms of t, but what we can put instead of dx. So we have x equals cos t, right? X equals cos t. So we have expressed dx in terms of dt, dx equal minus sin dt. Now, the reason for finding this dx is that we have to integrate in terms of t, because y is in terms of t. So we substitute this expression in place of dx. So the integration becomes y, and y, our question says y is minus cos t, and dx turns out to be minus sin t dt. And the limits are pi by 6 to pi by 4. Okay. Now, here's where things get interesting. We have cos t, sin t. We have cos t and sin t, and we have this integration sign and the limits. We have to integrate in terms of t with respect to t. Now, what we have to do is we can't integrate products at this stage. So we have to identify that this expression, this identity, can be written as a single trigonometric ratio. How is that? We should remember that sin 2t equals to sin t cos t. From there, sin t cos t turns out to be half sin 2t. So instead of sin t cos t, we can write half sin 2t. Now we can integrate this function, this expression in terms of t, and it turns out to be 1 by 8. So my purpose here is to explain the different types of integrations and to bring the integration to a step from where we can integrate it very easily. So using these two examples, you should now be able to do exercise number 6a. If you have any confusion with any particular math, please do let me know. I'll solve that math for you. Moving on to section 6.2, where we have the volume of revolutions. So for volume of revolutions, the general formula is we integrate y square with respect to dx. Okay. So example number 3 shows an integration where we have a Cartesian equation. So I'll not be going there. I will jump to example number 4, where we have a parametric integration. So in the same way, just like the integration that we did a while back, y square dx. So y is already expressed in terms of t. So y is not the problem. The problem here is dx. We can't integrate in terms of x because y is in terms of t. So we have to integrate in terms of dt. So the formula here turns out to be we have to substitute this dx in terms of dt. How do we do that? Looking at example number 4, we have x equals 2t. So dx by dt equals 2. From there we get dx equals 2 dt. Right. Now integration of y with respect to dx, y we have t square and dx is 2 dt. And the limits, they have told us the limits to be 2 to 4. Please mind it, we will do the same thing, same concept in upcoming examples. But the question will not always tell you the limits in terms of t. Sometimes the limit will be given in terms of x, and then we have to convert the limits to t. And we will do this type of math very shortly. So now this is a form that we can integrate very easily, and the answer turns out to be 1984. Oh, so first of all, we have a 2 pi over here. I missed this 2 pi. So we have this 2 pi here. The answer turns out to be 1984 by 5 pi. I'm very sorry for missing this 2 pi. For the volume of integration, we have integration of y square dx, and we have 2 pi outside. So using this concept, you should be able to do example number 5. Okay, but example number 5 needs some sort of explanation because it says it does not give us the values of the limits directly. We have to determine the values. Now, how do we do that? The question says that the curve cuts the x-axis at points A and B. So we have to find the volume of revolution about the points A and B. This is our key point, that the curve cuts the x-axis at points A and B. So how do we find the coordinates of the points where the curve cuts the x-axis? By putting y equals 0. And if you put y equals 0, we have, this is example number 5, we have t square minus 1 equals 0. Sorry, t square minus t equals 0, and we have t equals 0 and 1. These are the two values of t that we have, and these are our limits for our volume of revolution. So using these two concepts, you should be able to do exercise number 6b, Once again, if you need any help with any particular math, please comment and I will try to do those maths for you. Coming to our third section, 6.3. Now we will be going to integration by substitution. So substitution means when we have to substitute some expression with some other simpler expression which we can integrate. If you had further pure math in O levels, then you could have done this type of integration in further pure math. I'll go with example number 6. Example number 6 is quite simple actually, because I already tell you what to substitute. Now, my target here is to give you some general idea how to determine which substitution to use. So, for example, in example number 7, you can see that we have this integration cos x sin x 1 plus sin x cube dx. This is the integration. So one general rule, it could work sometimes. It's not a general rule. It could work. It works mostly. Might not work all the time, but it's a rule. Rule by observation. It works commonly, and the rule is that when you have some function inside a power, for example, we have 3 over here. We put this expression as our substitution. So u equals, as they have run in the question, 1 plus sin x. This is the substitution that they have used, 1 plus sin x. And from there onwards, we can move on very easily. This is the step that we need in order to substitute dx. Dx is our main problem. So first of all, we do du by dx. Du by dx equals cos x. So dx equals du by cos x. Perfect. Now what we have to do is, we have taken 1 plus sin x as u, right? 1 plus sin x as u. Now, this tells us that sin x equals u minus 1. So this step, from here we have cos x. So let us leave cos x as it is. Let us leave everything as it is. Sin x, 1 plus sin x whole cube du by cos u. Du by cos x. So the reason that I've left everything in terms of x is because I need to simplify these cos x and cos x. So if you are already substituted the x functions, the x expressions in terms of u, you would not be able to cancel this cos x and this cos x out. So we cancel out this cos x, and we have finally sin x 1 plus sin x whole cube du. Now the problem here is that we have integration in terms of u, but still we have x in our expressions. What we have to do is, we have to use this substitution over here. So sin x, as we have seen here, sin x can be written as u minus 1, and 1 plus sin x whole cube can be written as u cube du. Now this is an integration that we can do very easily, but here's a catch. What we have to do here, we don't have to do it, there's no catch here, but there could be a catch. The catch could be, which we will see in upcoming examples, the catch could be, suppose that they had put the limits in terms of like this, something like this, pi by 2. However, now we are going from x to u. We are going from x to an integration in terms of with respect to u. So we would have had to change our limits in terms of u. How do we do that? You write x here and u here. The values of x limits are pi by 6 and pi by 2. And what is u? U equals 1 plus sin x. So you substitute pi by 6 once, and then you substitute pi by 2 to get the two values, the two limits of u. And then you put these two values, 1 and 2, over here, u1 and u2. These would be your limits. So let us try to see if there is an example. Yes, we have an example in example number 8. Once again, as I told you before, a rule of thumb which might not work all the time, such a rule is that if you have an expression inside a bracket and with some raised power, we take that as our substitution. So for example, if you want to integrate to 0 x plus 1 whole cube dx, so we have this little power over here, right? So this x plus 1 will be our substitution. This will be a substitution. And then we move onward with the math as we have done in example number 7. But here's a small catch. The catch here is that we have to change the limits from x to the limits of u. How do you do that? We write x and u as I've shown in the previous example. X is from 0 to 2 and u goes from x, u is x plus 1. So 0 plus 1 is 1 and 2 plus 1 is 3. So the limits now are no longer 2 and 0. The limits would be 1 to 3. These are the new limits, and we do the substitution of x and dx as we have done in the previous examples. Another rule of thumb that we can see here is that we have taken the substitution in part B of this question as 1 plus sin x. So I had told you a while back that if you have some expression inside a power, for example, in example number 8b, we have 1 plus sin x inside a power. That power is 1 by 2. It is a power. And we have cos x outside this, and we have this integration here. So what we have to do is we have to take 1 plus sin x as our substitution. That is u. So it's a rule of thumb that if we have some expression inside some power, we will take that expression as our substitution. So once again, if you face any particular problem with exercise number 6C, please let me know. I will try to clear those maths for you. Coming down to our final section number 4, 6.4. What we have here is integration by parts, but for some particular type of math, I will show you one example, integration by table, integration by parts using tables that you can use to do your integration by part. It will not work all the time, and I'm showing you exactly when it will work. For example, if you have an integration that goes like this, x to the power x cube cos x dx. Suppose this is your integration. This is your integration. Integration by parts using tables works like this. You have your u here and you have your v here. The u will be x cube. The v will be cos x. So you choose u in such a way, the u should be chosen in such a way so that it can be differentiated until it becomes 0. So this method that I'm showing right now will only work when you have some sort of expression that can be differentiated repeatedly until it becomes 0. For instance, cos x can't be differentiated until it becomes 0. It will be sin x, then again cos x, sin x, cos x, sin x, cos x, and so on. However, if you keep differentiating x cube, it will become 0 at one point, and we'll see how. In the first step, when we differentiate x cube once, it becomes 3x squared. When we differentiate 3x squared again, it becomes 6x, and then it becomes 6, and then it becomes 0. So here we have it. However, for v, you will not differentiate, you will integrate. So integrating cos x, we have sin x. Integrating sin x, we have minus cos x. Integrating cos x, we have again minus sin x. And integrating minus sin x, we have positive cos x. And we will stop as soon as we reach this 0 level. Next step in this method is to draw this type of lines, and I will show you why I have drawn these lines. And then put your signs like this, plus, minus, plus, minus. The target here is to do this, x into sin x, x cube into sin x, x cube into sin x. And what is the purpose of this plus here? The plus purpose is that I will multiply plus 1 with this whole thing. I will multiply plus 1 with this whole thing. And then we have 3x squared into minus cos x. So 3x squared into minus cos x. The purpose of this minus is that I will put this minus over here. This minus will go here and this plus will go here. Okay, then we have 6x into minus sin x. So 6x into minus sin x. And here we have a plus, so we put this plus over here. Again, 6 into cos x, 6 into cos x. And here we had a minus, so we put a minus over here. Ultimately, our expression turns out to be x cube sin x positive minus minus plus 3 x square cos x plus, we have minus, plus into minus is minus, minus 6x sin x minus 6 cos x. So this is our integration. Now this only works when you have some expression that can be differentiated until it becomes 0. So you can apply this to example number 9 and to example number 11. That's it. Example number 9 and 11, you can apply this method. Now we will be looking at an example where we have to use the integration by parts, but we can't use the formula that we just saw. That example is example number 12 that we have. Example 12. Example 12 says we have to integrate 1 to 2 ln x dx. Ln x dx. Okay. So first of all, our formula for the derivatives are, if we want to integrate u dv by dx, we have dx, we have uv minus v du by dx into dx. So we have to determine, for determining our integrant integration, we have to determine u, v, and du by dx. Okay, and as of here, we have to choose u in such a way so that we know the differentiation of that expression. Or in other words, you have to take that expression as u, which is easier to differentiate than to integrate. So we don't know the integration of ln x, so we will take ln x as our u equals ln x, and we very well know the derivative of ln x, so du by dx equals 1 by x. So we have already found du by dx is found. Now we have to take dv by dx. We don't have any other expression with ln x, so dv by dx is equal to 1. From there we can integrate 1 very easily. So the integration of 1 is x. So we also know our v. So v we know, and u we also know from u equal to ln x. So we know all the things that we need to put into our formula. The formula, putting this into the formula, we have uv. What is u? U is ln x. What is v? V is x. So uv, that is x ln x, and we put the limits to 1 minus integration of v du by dx. So what is v? V is x, and u by dx is 1 by x. 1 to 2. So here we have 2 ln 2, because ln 1 equals 0, and here we have the integration of x. Integration of 1 gives us x 2 to 1. Finally, our answer turns out to be 2 ln 2 minus 1. So this is how you apply this formula in this type of integrations. But if you have an expression that can be differentiated all the way to 0, you can apply the tabular formula. It will make your work very simple. Okay. Sometimes there are expressions which we don't know whether they're easier to integrate or to differentiate. They're equally easy to integrate and differentiate. For example, we have example number 13, where the two functions are ex and sin x, and we don't know which one to take as u. Which one to take as u. So we have to follow this late acronym. L stands for logarithms, A stands for algebraic functions like x cube, x square, root of x plus 1, T means trigonometric functions, and E means exponentials. So since exponential comes at the bottom, so we will take our u as the exponential, that is E. That is how this rule works. Okay, so u equals ex, and dv by dx equals sin x. Okay, so du by dx over here is ex, and v is minus cos x. Minus cos x. From here, we can apply the formula very easily. The formula is the integration equal to uv minus v into du by dx. Okay, so what is uv? U we have the e to the power x, and v is minus cos x. We put cos x here and the minus over here, and we don't have any limits, so that's good for us. V is minus cos x again, and du by dx equals e to the power x. Dx. In the next step, we can write e to the power x cos x minus plus integration of e to the power x and cos x. Once again, for the second time, we have a situation where we have to apply integration by parts. Integration by parts. So once again, we take our u as e to the power x. For the second part as well, we take our u as e to the power x and our dv by dx as cos x. So our du by dx equals e to the power x and our v equals sin x. Applying the formula again, we have our integration uv minus integration of v du by dx. Okay. So uv, what is uv? uv equals u is e to the power x and v is sin x. Okay. And integration of v du by dx, v is sin x, du by dx is e to the power x. Okay. Now look closely, that this is the initial or the original integration that we wanted to find out. Okay, this is the original integration that we wanted to find out. So as of now, we had one I over here. We had one I here, and our final I, the initial I, this is I2 actually, I2. The initial I, the I that is equal to this, was minus e to the power x cos x plus this I2, which is e to the power x sin x, e to the power x sin x, minus integration of sin x e to the power x dx. Now, we know that our I is the integration of e to the power x sin x dx. Now, once again, we have this expression over here, e to the power x sin x dx. So, this can be written as I cos x plus e to the power x sin x minus I. From there, we have 2y equals, we take e common, so sin x minus cos x. From there, we have our I equal to 1 by 2 e to the power x sin x minus cos x, and since it's an indefinite integration, so don't forget to put plus c. So now you should be able to do exercise 6D using the concepts that we have learned here. In the next class, we will learn how to do the integration of partial fractions. We also have differential equations and modeling using differential equations. And after that, we should be done with this chapter. So please be very sure to thoroughly practice up to exercise 6D. If you want me to solve any particular math of a particular exercise, please comment below and I'll try to solve it for you. Thank you very much for watching this video.